doctor. I'm not a professor. I'm doctor. That's okay. Can you hear me? So I'm going to have a pretty much follow-up talk on Brian and Jeff's and also on Rachel's talk from yesterday. And I'm going to talk about the evolution of the stellar astrospheres in time. And while Brian and Jeff covered what happens outside and in the boundary, I will discuss the changes from the star to the edge of the stellar system and what's their impact on the different things. And the outline is essentially, I will start with just discussing what's dominating or control the structure of the astrosphere, and what are the parameters that change it in time. Then I'm going to discuss something that also was mentioned, cosmic rays, the transport of cosmic rays and particles, high energetic particles in general in the solar system and the impact of the changes in the astrosphere on the transport. I'll briefly discuss the effect of these changes on the evolution, disk evolution, when in early stellar systems where the stellar system is still evolving. So this will be the first part. The second part will be focused on coronal mass ejections and how changes in time affect coronal mass ejections. I will discuss the changes in the initiation, the propagation, and the evolution of CMEs with time to different astrospheres. Then I'm going to discuss or extend the effect of CMEs or the role of CMEs in stellar mass loss rates and stellar spin down. And finally, I'll discuss coronal mass ejections and exoplanets. So the relevant chapters from the books are shown here. There are some parts of other chapters that are relevant because it's all plasma physics and space physics, so there are many things that are relevant from other chapters. But these chapters really discuss the topics I will talk about in the context of the solar system. One thing I would like to, is two comments actually. I may just transfer between stellar terminology to solar terminology, meaning solar wind versus stellar wind. Usually I will mean the same thing. So if I transition between them, it's just a matter of the fact that I don't pay attention too much. And the other thing I would like to mention is that a lot of the stuff I will discuss here is an ongoing research. We don't know much. These are kind of suggestions what will happen. But we don't know much about many of the things I will discuss about. So it's really a cutting-edge research that is just starting. And because it's essentially an implementation of space physics and solar physics to astrophysics, we have very few observations, like Brian's observations, that we can even constrain the framework we're working. So this is an important comment to make. So astrospheres in time. I won't spend a lot of time on that. We already know that stars, as they evolve, they move along the HR diagram. They become less active, especially solar analogs. They're very active. They have fast rotation when they're young. They have high stellar activity. And as they grow older, they spin down and they lose some of their activity level and they become more quiet stars. And we have the M dwarf branch here, which are more active than the sun, and we have the giants, of course, which are, we can assume that these are different types of stars because they don't have the same type of stellar winds and they don't have the same type of stellar corona. So the focus of my talk is on solar analogs. Again, I would argue that we can, better? Okay. I would define the solar analog in this context as stars with hot corona and thermally driven winds in general. So these are solar analogs as far as I'm concerned. We're already seeing these plots that show that there's a relation between the rotation of the star and the age and also the stellar activity here on the right. This is a function of the Rossby number, which is a representation of the stellar rotation. So in general, we have we do know about stellar relations between the rotation, the age, the stellar activity, and magnetic fields. Now, if we think about the sun and the solar wind, we have the solar magnetic field, which you can assume it's to first order that it's a dipole. And then we have the radially expanding solar wind that stretches the field, the magnetic field with it, because this is a plasma, and we assume it's a pure MHD plasma. So the conductivity is infinite. So the field is frozen to the plasma because any motion, any changes in the magnetic field that the plasma will do, the field will adapt really, really quickly. So if we change the plasma around the magnetic field, we can imagine that the field is glued to this magnetic field. So the stellar wind stretches the magnetic field out with it, and eventually it opens up in a point where the wind velocity equals the local alpha speed. So we have this configuration of these stretched and eventually open field lines in the radial direction. And if we look at the solar system from the top, the combination of this radial propagation with the solar rotation, because these field lines are anchored to the sun on one end, gives us a spiral configuration. And you can imagine that this hand is the sun and is rotating like that. And there's a parcel of plasma that leaves the sun in the radial direction, but the sun continues to move. So in the frame of reference rotating with the sun, these field lines will be stretched this way. So that's what we have here. We have this Parker spiral. It's similar to a rotating sprinkler. So we can write down the equation that describes this Parker spiral. If we assume that in the frame of reference rotating with the sun, at some point the field is open and it's fully radial, so we can equate the two components of the azimuthal component and the radial component of the magnetic field with the same components of the velocity. Here we assume that there's no theta component. And this ratio, the radial speed of the stellar wind is simply the stellar wind velocity. And in the azimuthal direction, it's simply the solar rotation times the location in the radial direction. And we have the sine theta because this component goes to 0 as we get closer to the pole. We can assume that this is 1. And we're talking about the equator for the rest of the talk. But I will keep this sine theta there anyway. So we can remanipulate the equation and get the equation for the magnetic field. And if we take the divergence of the magnetic field equals to 0, we get this equation for the structure of the magnetic field line in the heliosphere. And this is the Parker magnetic field. It's based on this Parker spiral topology of the magnetic field in the heliosphere. One thing to note is that we have R component that goes like 1 over R squared, while we have this extra R here in the phi component. So the phi component drops like 1 over R. So it drops slowly. So as we go further out in the solar system, the azimuthal component of the magnetic field become to be more and more dominated. And at the Earth, it's about 45 degrees. And by the time we reach Jupiter, it's already essentially fully azimuthal field. So one thing to note is that there are several parameters here that will determine the particular magnetic field lines. We have this BS, and BS is the magnitude. So let's start. We have RS. The RS is the point where we assume the field line is radial. You can think about this distance as the alpha point, where the velocity of the solar wind equals the alpha speed, so the field line is open. You can also think about this R0 as the point where the wind is fully developed and is not accelerated anymore. It achieved its asymptotic speed at that point. And BS is the magnitude of the magnetic field at that point R naught. So we have these two parameters here. We have the stellar rotation, which can change for other stars. And we have the solar wind velocity, which can change as well. So let's discuss how the different parameters may affect the astrosphere. Now I switch to astrosphere, which is like the heliosphere, but for other stars. And see how these parameters change with time. And for larger distances, I eliminated this R minus R naught here and left with only R, because R is much greater than R naught. So how does the stellar rotation affect this structure? We know that young stars rotate much faster than the current sun. The current sun has a rotational period of about 26 to 27 days. young active stars can have rotation period of 2, 1, half a day rotation. They rotate really fast. So let's see how this, the field line structure in the heliosphere changes for fast rotations. Here on the right, I show a simulation of a dipole magnetic field with stellar wind. And here the rotation period is 25 days, solar-like. And you can see that overall the field lines are simply radial. The domain size is about 24 stellar radii, the radius of that particular star, which in that case was the sun, or the solar size. If we boost we repeat the same simulation, but we simply boost the rotation period of the star to half a day rotation. There are stars that rotate with that fast. You can see that even within the corona, the azimuthal component of the field completely dominates the corona. We have this wrapped field all over, and there are many consequences for that structure, and I will discuss it in the next few slides. And here I just did a solution for a spiral where I changed the rotation period from 25 days for the blue line. It was 10 days for the yellow and 4 days for the red. And again, you can see that the tangling of the field lines is much increases as we increase the rotation. And of course, for the extreme case of half a day rotation, you can see that it completely dominates the corona. So the rotation, the change in the rotation period has a clear effect on the structure of the heliospheric field. Another thing I would like to mention is that if we're increasing the wrapping of the azimuthal field line, this will increase the overall magnitude of the magnetic field because you compress all the field lines together. So you boost the magnitude of the field line of the astrospheric magnetic field everywhere just by increasing this rotation. Let's now discuss how the changes in this B, the source B magnitude changes with time and with stellar evolution. Keep in mind that that equation describes a single field line. So of course we have a collection of magnetic field lines in the sun, and each one of them may have this different value of B. And indeed, if we look at the magnetograms during solar minimum, solar maximum, during solar minimum, you can have this dipolar structure of the solar magnetic field. These are measurements of the radial magnetic field at the surface of at the photosphere from the Wilcox Solar Observatory. You can see the dipolar shape during solar minimum, and during solar maximum, you can see it's not dipolar anymore. It's tilted, and it has many different things. You can imagine that if we collect each field line here, and here the overall structure of the heliosphere will be very, very different. And indeed, we have many, many observations that infer that indeed the solar wind structure essentially follows the structure of this magnetic field at the surface of the sun. Now, in addition, we also have a dependence of the solar wind speed on this value. So not only we have a specific value for BS at each point, we also have a different value for U for the solar wind speed. So that has another effect on the structure of the particular field line for each and every given point in the solar corona, because it will be different from one another. Yeah.
Are you implicitly assuming that the magnetic field?
Yes.
Because in the very active stars, rapid rotators, our diffraction rate will make
Of course, and I will show it, yeah. But of course, it's because the azimuthal component becomes very dominant all the way almost to the surface. Yeah. Yes, Carl. Yes. Yes. Yeah, the comment was that This is not really the radial field on the surface, but it's a representation of that based on that particular measure. And this kind of measurements that we use to drive the global models for the solar corona and stellar corona as well. Usually this is the input, or one of the inputs. Now, in the next few slides, I will discuss, if in the context of stellar evolution, how the change, what's the effect of the change in rotation period or rate, and I want to discuss changes, relatively short period changes in the magnetic field, like the solar cycle. I will discuss more how the overall structure of the magnetic field we observe in different stellar types will affect the distribution or the structure of the heliosphere or astrosphere. As we just mentioned, young active stars, they're fast rotating, and they have their magnetic activity concentrated at high latitude, and that was shown by Carl yesterday. And here I'll show two examples. We have AB-Dor. It's a young solar analog with a rotation period of half a day, just like I showed. And this is the Zeeman Doppler imaging map that was mentioned here, taken by Gete Hussein, that shows the radial component of the magnetic field of that stars. The Zeeman Doppler imaging method essentially combines Doppler imaging that tells us where there are darker spots or darker regions with Zeeman measurements of the magnetic field or the Stokes components of the polarization. And from that, we can reconstruct tentative low-resolution maps of the magnetic field of stars. It can be done mostly for fast-rotating stars that we can see these features coming back many times within the time that the observation was taken. And you can see that the red and blue colors represent the opposite polarity, but you can see that the high concentrations are located at around 50 or 60 degrees from the equator. On the sun, we usually see the active regions not higher than 30 or 40 degrees in latitude. So, and we see it also in other stars that the magnetic activity seems to be concentrated at high latitudes from the equator. So again, it's a reconstruction of the radial component of the photospheric field, which is again a tricky thing. Again, they combine the Doppler measurements that give you regions of darker and brighter areas, and then on top of that, they take Zeeman measurements, and that gives them they measure the Stokes components, which is the polarization of the light that goes through a magnetic field. In principle, you should measure 6 components. They measure 2, or they have certain 2 components, and actually this is the reason why there's a lot of criticism about this method, or there's a lot of uncertainty. But we use it just to get a general idea about the structure. And the combination of these 2 measurements enables them to reconstruct these kind of maps. And of course, it's very low resolution because you're trying to resolve a point source. But with that respect, they claim to have enough resolution to do this kind of maps. Yes? No, so the question is there another way to obtain the magnetic field, essentially? And the answer is it's extremely hard to measure magnetic fields in other stars because they're so far, the signal is so weak, etc. There are some attempts to measure the dipole components using radio measurements. With this method, you need to have very strong fields and fast rotation so you can even distinct a signal from whatever you have. So it's very, very hard. And as I mentioned, there's a lot of uncertainties in these maps. But what you can do is you can clearly see that you have more stuff at certain latitudes than in the other part. And I don't know if you notice, this goes all the way to minus 30 degrees, and this is because we don't, the inclination, so we don't see the other part of the star. But there's a clear distinguish between this part, which is pretty much blank, to the high latitude here that is full of supposedly strong magnetic fields. And we see this kind of behavior occurring in many other active fast-rotating stars. So we're pretty confident that this behavior is pretty consistent. Yep. Okay.
The limitations on the technique are also related with the spectral resolution capacity. If it's really fast for the we can disentangle the biometric signatures. Right now, it's much more modern spectral. Go into a little bit lower, not so fast for the a little bit better right now. But also you combine different techniques, just as Ofer said, like the Doppler imaging techniques.
Yeah. This is actually simulation that CAR did with Alan Teitel in 2001, where they embedded flux emergence for this kind of fast-rotating stars, and they help to explain why this activity is concentrated at high latitudes. So that's what I'm showing here. This is not real observation. So the question is, how does the fact that for young active stars we have the activity concentrated at high latitude will affect the overall structure of the astrosphere? And this is a simulation I did where I took a solar magnetogram with the active regions which are shown here in yellow and blue. This is an active sun of the year 2000. And these are the active regions. They're very close to the equator. And you can see the three-dimensional magnetic field lines inside the corona. And then I split the magnetic field between the weak dipole component and the strong active region component. And I shifted the active regions in latitude by 30 degrees and then by 60 degrees towards the pole. And you can see that the overall structure of the magnetic field in the corona changes dramatically only due to that. So the location of the magnetic activity for young active stars significantly changes the overall structure of the heliosphere or the astrosphere. You can imagine that in this case, the polar field all the way to the astrosphere will be much stronger than in this case. Here we're talking about 5 Gauss, 10 Gauss polar field of the sun. And these active regions in Abidor can reach 2 kilogauss in size. So significantly stronger fields in the polar regions. This is actually an MHD solution, but the initial condition was a potential field, and it looks pretty much the same at these distances. So now, let's discuss a little bit transport of particles in the astrosphere and how the changes in time modify the transport of cosmic rays. Again, it was mentioned by Carl yesterday and also by Rachel. Galactic cosmic rays are generated. Oops, I actually have a picture. There we go. We think they're usually generated in supernova, where you have very strong shocks that accelerate particles to energies that are very, very high. These are EVs. So you can see galactic cosmic rays energy goes from 1 GeV to 10 to the 21 EV. Very energetic particles. And they have a particular spectrum that has been explained for many years by different models. The general transport equation for galactic cosmic rays was introduced by Parker in 1965. This is a very generalized equation. And overall, it describes the diffusion term, and you can see this kappa here. This kappa, I think there's 30 years of work just to try to describe what this kappa is and how it behaves. And using that, trying to explain what we see in the heliosphere. We have an advection term. This is the guiding center drift that was mentioned by Tomas, who already left. This is the overall drift that the particles have as they gyrate, this kind of motion. And this is important for a reason that I will show in the next slide. We have an energy change term, and of course, losses and sources, because we can have losses and sources. And again, these are extremely generalized. We know that cosmic rays are modulated by the heliosphere. There's a clear anti-correlation between the solar cycle, which is shown here, and the flux of cosmic rays. You can see that the peaks are near solar minimum. The reason for that was essentially a ongoing homework question yesterday. So I can essentially wrap it up. The reason for the reduction of the cosmic rays is as we go to solar maximum, the level of turbulence in the heliosphere goes up. We have more slow solar wind in the volume, which is more sporadic than the fast solar wind. And overall, we have much more turbulence going on. And that pushes away the cosmic rays via the diffusion term, via this kappa. The other reason is that we have much more CMEs. They generate shocks in the heliosphere, and these shocks sometimes interact with each other. Again, they increase the level of turbulence in the heliosphere, and again, that pushes away galactic cosmic rays. And finally, we have an increase of the polar field during solar maximum. That also pushes away the galactic cosmic rays. You can see here, this is interesting, that you have a transition between a peaked high intensity to flat high intensity and peaked and flat. And the question is why that occurs. So that actually related to the drift term that I just mentioned in the last slide. So the drift term depends on the direction of the magnetic field in the heliosphere, and the direction is flips every 11 years. And what happens is these are the drift patterns of cosmic rays, and it's marked by the A larger than 0 and A smaller than 0. A is essentially the direction of the magnetic field. And you can see that during periods that A is smaller than 0, which is here, you can see that the cosmic rays get into the heliosphere along the equator, where it's just harder for them to get there. There's more turbulence. There's more stuff to go through. So you get this peaked flux during this time, while during the times that A is larger than 0, you see that the drift motion inwards coming from the polar regions, where it's much easier for cosmic rays to penetrate. So that's a direct consequence of the drift motion. And galactic cosmic rays help us to think whether Voyager has already left the solar system or not. I just had a discussion with Margie about this. We don't know yet. It's still a debate whether Voyager 1 is outside of the solar system or not. But one thing we can clearly see is that as Voyager approaching the edge of the solar system and being inside the intermediate region, we can see a clear increase in the cosmic ray flux and a clear decrease in solar wind flux. So this shows that at least we're on our way to be out. Now, galactic cosmic rays has an effect on the evolution of the Earth, and this is related to the early solar system and the fact that we would like to see how the astrosphere or the heliosphere used to be when the Earth was formed. And in particular, galactic cosmic rays may have some important effects. First, they serve as an ionization source for production and creation of complex molecules. They also they have an impact on cellular mutations, either direct or indirect. We know nowadays that cosmic rays trigger lightnings, which is very important. And there is a controversial issue that some people claim that cosmic rays have a net cooling effect on the Earth. So if you reduce the amount of cosmic rays, you can get an increase in the overall surface temperature of the atmosphere, and that's related to climate change. It's considered to be anti-global warming theory, but it's still under debate. There are some recent experiments in CERN that they try to confirm this process. The bottom line is that they confirmed the experience, but atmospheric physicists claim that looked nothing like a real atmosphere. So that's science. But it's important to mention this aspect as well. We're going to look now at a period of the Archean Eon, about 3.8 billion years ago. And why this time? This is right after the late heavy bombardment, where all this stuff in the solar system kept hitting the Earth. So at that time, the solar system was quite clean from small bodies. And that's the period where we have the first fossils appearance. So that's the period where essentially life started on the Earth. And it's important, so we would like to see how the young sun used to be during that time and how the heliosphere looked at that time in the context of cosmic rays. So the rotation period was probably about 2 to 4 times faster than the current 27 days period. And we should expect higher level of activity because it's a young star, so it's more active, especially if it's rotating faster. So again, here I mentioned again what I did. This is now a theta display of the magnetogram of the active sun that I showed before in the 3-dimensional view. And this is the original magnetogram that I took. And these, again, are the active regions that appear on the original map. And then I just shifted these 2 belts of active regions by 30 degrees and by 60 degrees in latitude towards the pole to resemble a young active star or young active sun, if you like, based on the actual solar magnetogram. And I used this input to simulate the structure of the magnetic field in the heliosphere at the time. And then I gave this solution to Joseph Cota from University of Arizona, and we calculated the cosmic ray transport from the edge of the solar system all the way to the Earth, and we calculated the fluxes for different parameters of the young sun. So for each case, we had this solution of the transport of cosmic rays or the spectrum of cosmic rays for a given set of parameters. And another thing I did for this solution, I boosted up, I had 2 additional cases where I boosted up by a factor of 5 the magnitude of these active regions and the magnitude of the ambient dipole or the weak dipole component of the magnetic field. So here are the solutions. This is the original solar magnetogram. This is the magnetogram where the spots shifted by 30 degrees, and here it's the spot shifted by 60 degrees. So this is a polar active regions. And you can see that this is the interstellar medium cosmic ray flux. So this is the boundary condition for the intensity of the cosmic rays at the edge of the solar system. And then for different rotation, you can see I have the different fluxes or different spectrum. And you can see that the most dramatic effect, of course, clearly is due to the increase of rotation, where you see that for a 2 days rotation, but just by increasing the rotation, we reduce the cosmic rays intensity at their peak by 2 orders of magnitude or so. So this is the main effect. There is some additional reduction due to the latitude of the spots, but it's not that much. However, if I boost the magnitude of the spots by a factor of 5, I get even further reduction. So the bottom line is that the cosmic ray intensity near the Earth during the period of the young solar system was probably significantly lower than the current days because of the fast rotation of the sun and because of the stronger magnetic field that it had at the time. I'll briefly go through the effect of this transport on stellar evolution and disk evolution. I'll just turn this on. Okay. Accretion disks around T Tauri stars. These are evolving young suns that have an accretion disk around them, and this accretion disk eventually will form the planets around the star. So there's the problem of angular momentum in a transfer within this. This is a long-standing problem because it's important to determine this transfer of angular momentum within the disk if we want to explain the formation of planetary systems and the origin of planets. Now, in 1991, and this was a quite open question for a while, in 1991, Barbos and Howley introduced the so-called Magneto-rotational Instability. And the idea was that we have magnetic fields in the disk, and these magnetic fields essentially attach two particles in the disk, and they serve as a restoring force. So these particles don't run away from each other. They keep attached to each other. And with a more detailed analysis, they showed that you can get the right transfer of angular momentum that was necessary at the time. This is an MHD formulation, so we assume that the disk is sufficiently ionized. But the question is, does the disk is sufficiently ionized? So this is something that is still under debate, especially recently. There are some recent... What? Oh yeah, I know what prize you mean. No, I think that's Frank Shu, you mean? Yeah, I know what you're talking about. I'm not sure how it is related to that. Okay, well, let's keep it to the end because I want to try to finish this before the break, okay? It's not a direct question about this. So we can have different ionization sources in the disk. This plot is more busy than needed. We can have simple thermal ionization at this part of the disk, the part that's close to the star, because there's heat there. There's also a lot of X-ray emissions from the hot corona, so that can serve as an ionization source. We can have galactic cosmic rays, and we can have decay of nuclei within the disk. But in many cases, the ionization will be mostly at the outer part, so we can have these dead zones inside that are not fully ionized or sufficiently ionized. And the question is, how does this instability works without sufficient ionization? So one thing me and Jeremy Drake did is to calculate the solution for the astrosphere of a T Tauri star. That we had a ZDI observation for that, so we could drive the model. And then again, we calculated the intensity of cosmic rays from the edge of the solar system based on the standard ISM intensity all the way close to 1 AU, which is here. This is a log scale of the radius in 1 AU. And again, we use different rotation periods, and you can see that even for a solar rotation period, there is a significant reduction by the magnetic field. And if it is a faster rotation of 4 days, which is a very typical rotation for T Tauri stars with disks, you can see that there's a significant, even more significant reduction of cosmic rays in large distances where the disk occupies. So can the disk be sufficiently ionized? This is a work done by Cleaves et al. Recently, where they tested or they modeled different sources of ionization. Here on the left, you can see the X-ray ionization. It goes from lower X-ray luminosity to higher. I think this is 10 to the 27 ergs per second, 10 to the 30, and 10 to the 32, I think. So the X-ray flux increases, and you can see that the fraction of the disk that is ionized, the blue parts represent the dead zones. You can see that the fraction of the dead zone is reduced as we go to higher X-ray intensity, as it should be. And here they also estimated the intensity of cosmic rays and the amount of ionization by cosmic rays, where the plot goes from top to bottom. The magnetic field increases. You can think about this way. So you can see that as we increase the magnetic field, this dead zone grows. And for a high, this represents a typical T Tauri star environment. And they expect that the ionization by cosmic ray, again, will create a significant dead zone inside. And again, the question is, can we assume that the disk is fully ionized to take this MHD approach and do some work with that, based on the fact that almost half of the disk is not ionized enough. So that's it. I think I will stop here. Yeah, so this will be the second part. I think it's a good time to stop. Are there any other questions?